Okay, so you've got two leaving groups. Which one's going to react first? Yeah. So your mechanism should account for that. The other thing is you could have easily come to the conclusion before I put up NMR data or a molecular formula that this is an elimination reaction. Okay, so I didn't give a temperature. Amines, alkyl amines like this are strong bases. So ammonia is a base. Amines then are also good bases. So you could have come to the conclusion that this does an elimination reaction. That would have been totally fair. That would be inconsistent with the NMR data I gave, right? So if you did an elimination, you get a double bond there and a double bond there. All the protons would be like 5 to 7 somewhere. Okay, so that's not it. So the first step is going to be an SN2. So you've got a primary halide, that can do an SN2 nicely. You've got a good nucleophile, that can do an SN2. You've got a polar aprotic solvent, that can support SN2. So the first step would be that. And you actually, so this gives you initially a salt. So you've got a cation, you've got an anion. And a question like this where I give you the reagents and I give you a product and you have to come up with a mechanism. So there's a little bit of forward and backward thinking. The forward thinking is, I've got a good leaving group, I've got a nucleophile, I can do an SN2 reaction. So do it. The backward thinking is, you've got a nitrogen attached to a methyl. Well, you've already got that in the reagent. You've got 4 carbons, 1, 2, 3, 4, bonded to leaving groups. And so really what you're thinking here is, you've got to make these 2 bonds. You've got to make those 2 carbon-nitrogen bonds. And so the first SN2, look at that. That makes a carbon-nitrogen bond. That's nice. So now you need that nitrogen to bond to this carbon. But you can't do that, because that quaternary positively charged nitrogen is not nucleophilic, right? A nucleophile is going to be an electron donor. Positively charged atoms aren't going to have electrons to give away. So how do we get that nitrogen to be a nucleophile again?
You lose the methyl?
But the methyl's in the final product. But you're on the right track.
Lose the hydrogen.
Lose the hydrogen. Yeah. Sorry I didn't get to you before everybody yelled it out. Right, so the next step then, and this is why excess methylamine is important. So the other thing that you might have been not forgiven, it's not a morality play. But if you'd had 2, like if you'd had methylamine, if we'd done this reaction here, and also down here, so that you had 2 nitrogens, that would be a pretty fair thing to think. Like if you're not given any data, and there's all these different possibilities, and I've said this to some of you, especially in those problems where it's like, oh, it could be SN1 or E1. It could be SN2 or E2. And you don't really, if there's not enough information, if there's not a temperature or something to guide you, then it really could be both of those. So I think that the first problem, the very first problem in that substitution elimination worksheet, right, it's a pretty sterically hindered secondary iodide, and you've got a really strong base. I give you a temperature, and I'm trying to use the temperature to point you toward substitution. But honestly, if you drew a good E2 product there and told me this is an E2 reaction, yeah, sure, fine. And I was on with someone this morning, like probably it would go, maybe 75-25 SN2. And if you want this substitution product, you lower the temperature. You make the reaction go a little longer, it goes slower, but you get more substitution. If you want elimination, you heat it up. Right? That's what I'd really like you guys thinking is not at this temperature, this reaction happens. Just lower temperatures give you more substitution, higher gives you less. So, like I said, in the absence of information here, if you did a second SN2 with methylamine on the bromide, that's okay. Once you get the experimental data, clearly isn't. And so now what will happen is methylamine is the base. It's both a nucleophile and a base. And so this winds up just being a Bronsted acid-base reaction, a proton transfer. So the nitrogen takes a proton, deposits that electron, the electron pair on nitrogen. All right, so again, if you're struggling with this, the curved arrow is going to originate on electrons. You don't have to draw that lone pair in, right? If you just draw an arrow from a neutral nitrogen, I know, your classmates know, everyone who knows chemistry knows, neutral nitrogens have a lone pair. Same thing with water. If you draw H2O and an arrow from the O, everybody knows that O's got electrons. So this arrow makes, and again, it points from nitrogen to the hydrogen, from the electrons to the partial positive. Hydrogen can't have two bonds, so then you take that bonding pair and make it a lone pair. Yeah.
Does it matter which hydrogen you bond to?
Not a
for
bit.
this version.
No. I mean, these two hydrogens, they're actually enantiotopic, but they're so again, enantiotopic atoms will react with achiral reagents completely the same. Okay, so then this is going to give us, this properly is at an equilibrium now. And we get minus. So we got that floating around. All right, so what's the next arrow? Why does it leave?
Oh, because the base is going to come in and kick it out?
Yeah. All right, so again, bromide's on a primary carbon here, right? So it's not going to be an SN1 reaction. That nitrogen, now that it's neutral again, now that we have re-neutralized, now that we neutralized the nitrogen, I guess. Now that this nitrogen is back to being neutral and a base, it's also nucleophilic. And so it can attack this carbon, kick out the bromide. We get another salt. Who doesn't like that? Just an opinion here. Not that you think it's wrong, you just don't like it. Okay. That's at least a few people are admitting it. A lot of students, I find, don't like these intramolecular reactions, right? So you've kind of been, either logically or you've actually been explicitly taught, reactions are A plus B. But you really should think about these functional groups as being separate, right? With just sigma bonds between these, there's nothing really. The alpha carbon with the bromide, it's like it's in a different molecule than the nitrogen, right? Functionally, it's not. It's really important to realize it's not. But this nitrogen is a nucleophile. The carbon's an electrophile, so they can react. Like if you have an acid and a base in the same molecule, they can react with each other. If you have a nucleophile and an electrophile in the same molecule, they can react with each other. And that's actually faster than the intramolecular reaction. All right, so this is an intermolecular reaction. Like this up here is an intramolecular, or is an intermolecular reaction. So that first reaction where the methylamine displaces the iodide, so for that to happen, right, a methylamine molecule wandering around in solution has to actually bump up against the backside of that carbon iodide bond. And that's a fairly unlikely thing to happen. And the only reason it happens with any appreciable speed is that molecules in solution actually have a lot of, they're flying around in there, right? They're not just sitting calmly. If you look at a calm glass of water, it looks like a calm glass of water. Like nothing's moving. But in fact, the individual water molecules are zipping around. Okay, so these two molecules have to just find themselves in a sea of other molecules. Whereas in that bottom reaction, the nucleophile and the electrophile are attached to each other. Okay, they don't have to go very far to find each other. So let me try this. I try this analogy sometimes. Clear your minds. Close your eyes. Yeah, who trusts me? I can see it now. I get visual evidence. All right, hit a human being. See, no, that's total violation of COVID protocol for one thing. That didn't just happen. Nobody hit each other. All right. And I didn't see it. I got distracted by people literally going after each other. That's never happened in a class before. You guys really are eager for human contact, I guess. Let's try this again. Hit a human being. There you go. You are a human being. Even in a crowded class, all right? So even when I have 60 people crammed into this space, it is still the fastest, it's not the most rewarding thing to do, but the fastest way to hit a human being is to hit yourself. All right, and that's essentially what this intramolecular reaction is, right? That lone pair is held, all these bonds are swinging around. If we actually draw that, all that has to happen is that arm with the bromide has to swing over, and then, like, this is exactly where it needs to be, bang and bang. All right, so I'm just trying to get, if you are thinking that reactions like this should happen, either proton transfers, those can happen intramolecularly, SN2, SN1, either of those, even E1 and E2, those can happen intramolecularly. Every reaction we talk about, if you look at it and you're like, wow, this molecule's got a nucleophile and an electrophile, if you really identify that, they're going to react with each other. Right? Because they're not making, the nitrogen's not here making a conscious choice, I want to hit my roommate or whatever. The bromide's not saying, I want to walk out on my roommate. Like, they just do this naturally. And so they're closer together. Effectively, their concentration is a lot higher. We actually call this an effective concentration. The concentration of alkyl bromide is really high next to this nitrogen. Okay, I think I've beat this horse plenty. So now what's the last step in the mechanism? Yeah, so the same thing again. Methylamines are going to come by, take that proton, neutralize. And again, it's a proton transfer, so it's reversible. Like, if you think about this, both of the proton transfer reactions are going to be pretty close in energy. So we've got a positive nitrogen, quaternary positive nitrogen, and a neutral nitrogen. After the proton transfer, we got a positive quaternary nitrogen and a neutral nitrogen. Right? Those are going to be, they're not going to be exactly the same, but they're going to be close to the same energy. Same thing for that last step. And so honestly, in this reaction, you probably neutralize at the end. Like, you'd probably work this reaction up with some base or something, some weak base that would pull that proton off. Questions about this one? Okay. Anything before I just keep going? Anything anybody wants to hash out? Chemistry-wise? Any problems been bugging you? You guys feel good? Is it just general paranoia, or like, yeah? You're saying there's nothing coming up. Yeah, it's a paranoid time of the world, I guess. All right. All right, give me a product of that reaction.
I have a question.
Mm-hmm.
When it's a double bond to
Mhm.
a carbon, it's still only a second degree carbon on that ring, right? Or is it,
Yeah, it would be secondary, but it's not secondary alkyl.
right,
It's different.
yeah.
It's a good question.
Yeah.
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 All right, another 30 seconds or so. So without looking at the substrate, the molecule with the leaving groups, what do the conditions suggest you would have? Right. You got a strong base / good nucleophile, temperature is low. So SN2 or E2 because of the strong base, good nucleophile, low temperature, probably going to be more SN2 than E2. This is sort of rehashing stuff I talked about earlier with the rate. 3 molar equivalents, so just 3 equivalents, that implies a molar equivalent. So if we have a mole of the product, the starting material on the left, we have 3 moles of lithium hydroxide, all right? Or if we have 0.2 millimoles, which is a more likely thing to have, then we would have 0.6 millimoles of lithium hydroxide. All right, so you've got leaving groups. How many leaving groups do we have?
Right.
I looked skeptical, did I? So you do. You've got 3 atoms that can be leaving groups. Okay, bromide can be a leaving group, chloride can be a leaving group, iodide can be a leaving group. But this bromide is not on an sp3 carbon. I don't know, and I don't know if that helps or not. No SN2 on sp2. Like, there is no SN2 on sp2. That is a true statement. But there's also no SN1. There's no E1. There's no E2. Okay, so there's a variety of reasons for that. And actually E2 is maybe, you can do eliminations to make, there can be E2. But it's a little complicated and we're not going to get into it this time. But there's definitely no SN2. Think about SN2, right? This benzene ring is planar. It's in the same plane as the bromide bond. The nucleophile's got to come from the back side. So the nucleophile would like have to plow through this ring. And it's hard for us to imagine the scale of a molecule. I mean, it's unbelievably tiny, but it's still a physical thing. It's not, a molecule's not, doesn't really undergo the kind of quantum things that an electron does, right? If you think about electrons themselves, they're in these clouds and you can't pin down exactly where they are because they're incredibly light. But even a proton, a single proton, is about 2,000 times heavier than an electron, which means these weird quantum effects really decrease. Once you get to the size of a molecule, there's essentially none. It's like, it really is like a little, for the atoms themselves, they're like bricks, okay? So this bromide, to kick this bromide out with a nucleophile, you'd have to blow through this, you'd blow the molecule apart anyway. So that bromide's not going to do anything under these conditions. Now, again, because you're all very sharp, you seem to like chemistry, if you take Orgo-2, you're going to see reactions where you can make bromines on benzene rings react. You can even displace them with nucleophiles. Okay, but you can't do it through an SN2 mechanism. The mechanism has to be different. That's all I'm going to say on that. I just, like I said, this is a small campus. If this was Texas A&M, I would just tell you these basic rules and I would go away and you'd never see me again. But I know that next spring you'd come upstairs from that nucleophilic aromatic substitution lecture and Amanda Jones would have told you that that bromide can be kicked out and you'd stop by my office and yell at me. So it's literally happened. Maybe not the yelling part, but I feel bad. Okay, so this bromide is not going to react. And I broke its bond anyway. All right. So now you're down to, I guess the other point of this question is you should consider these functional groups separately. Right? That tertiary chloride is going to do whatever a tertiary chloride does. It's not going to matter if there's a primary iodide in a benzene ring there. So, what's the tertiary chloride going to do?
E2.
It's going to do an E2. So the conditions sort of say SN2, but that chloride can't do SN2, right? Tertiary halides can't do SN2 reactions. And so it's going to do an E2. And then I would just say that's going to do an E2 and just give the Zaitsev product. Okay, so hydroxides are as small a base as we can really have. And so it's a strong base, it's small. So just give the more stable alkene here, which is going to be this one, right, where we've made the alkene, we've got the big group on one carbon, trans to the big group on the other carbon. And then we've got, and I'm going to recommend you number these, because I always screw these up. 1, 2, 3. So we got 5 carbons there. So what's the primary iodide going to do? Right, it's primary carbon. It can do SN2 just fine. Low temperature, really small base. So SN2 is probably going to happen out there. So this is going to be 1, 2, 3, 4, 5. All right, and then you can double check that with your numbering. You get one equivalent of lithium chloride, one equivalent of water, and one equivalent of lithium iodide. So on an exam, you wouldn't have to draw me any of those things. Okay, so you don't have to give me sodium chloride, sodium bromide, unless I specifically ask for it. It's an organic chemistry class. I want to know about the organic molecules. Right, so you get this alcohol. questions about that one? So that was all I was gonna talk about, so I'll just take questions, or if you don't wanna ask questions, either individually or en masse, you can go if you want, but you can also stick around and ask questions.
So why can't I know the bromine can't do substitution, but why can't it do elimination, other than temperature being low?
This particular one, so like I said, this does have, I realized, so this one's not Orgo 2, this one's like next section. You can actually do elimination here. It takes a really strong base, and it's not a great reaction. And you can generate an alkyne. That actually does happen. So the answer is that, yeah, that not doing E2 is pretty particular to this one, because now if you look at this, right, so if the base kicks that out, and this, the book, if I were teaching your, this is called a benzyne. And this is one where, so if you look at that, you should think that looks like a fairly unstable molecule, right? So what is the hybridization of these two carbons? Okay, what's the geometry of those two carbons? Bull. It's like, it's not linear, it's circular. So, right, so like this goes back to ring strain, right? You know, the 3-membered ring, what's the bond angle? And everyone's like 109.5. No, it's a triangle, look at it, it's 60. So geometry trumps bonding. So that is, those two carbons are not linear. Those two carbons are a long way from linear, right? Linear would be 180, the bond angle here is 120. Effectively what that means is that, and so here's where I get into it with my colleagues. I haven't pulled all of them, but I know enough of them who just teach that. The book shows it this way. The book's always shown it this way. Benzyne, 6-membered ring, 2 double bonds, 1 triple bond. So it is really unstable. That thing reacts like crazy. You can't isolate a benzyne. In fact, though, so there's a resonance structure. All right, we can draw a resonance structure here. You can always do this with a pi bond, but it usually doesn't matter. You can draw a resonance structure where the pi bond, there's not a second pi bond, you just have 2 radicals, 2 singly occupied orbitals on those carbons. And if you look at the chemistry of benzyne, it actually fits that resonance structure better